Hello, good day.
Hey, hey, Richardo, how you doing?
I'm fine, thank you. What about you, James?
I'm good, I'm good.
It's nice to meet you.
Nice to meet you. Hey, Mike, hey, Tony,
Hey, how's it going?
it's good.
Hey guys,
Hello, everyone.
We, hey, Andrew.
everybody, let's give everybody a minute or two, see if anybody else is going to join.
Yeah. I think KK and someone from Applied Materials should be joining. They say they're going to share with the Applied Material database today.
I'm
Yeah,
sorry,
it's-
KK and who else?
I think he said he will introduce someone from the Applied Materials database teams.
it's me, Riccardo. Well, at least I was invited by KK this for this session, so to present at least what we have and what we use in our
Ah, okay.
software.
That's
Okay.
good. Welcome, Richard.
Thank you.
Do you know if KK will be joining also?
No idea actually.
We just met him, I think, at another meeting earlier about an
Okay.
hour ago, so we're not sure. We didn't ask him, so we assume he might be joining, but
Let me try to chat to KK.
okay. Tony, do we have most people here, or shall we go ahead?
Oh, well, KK is saying that is having some troubles with Zoom. Let me share to him the link I'm using, so maybe he can get in.
I see. It should be the same Zoom he using though earlier. He was, yeah, joining from. Tony, do you have any updates? Or anything from your end side before we start with the applied material presentation?
Hello. Sorry I'm late. Zoom is giving me some issue. Thanks.
Hi, KK. Hello.
Hello.
Hey, KK.
Hello.
To have you here. All right, seems we have most people here. Tony, are you still there?
Sorry, I'm muted.
Yeah.
Yeah, no. Why don't we get started? So I guess Applied Material was gonna do a presentation today to what specifically were you going to talk about, Ricardo?
It's yeah, probably the material property database that they have. We talk a bit right before. I think they can introduce that. Before that, so we maybe like do a quick intro for Richard or
Yeah, yes. So maybe I can start share the screen. I have a short introduction of what we do and in which context we use material database for the group basically where I'm part from. So
yeah, go ahead and share your screen, Richard.
yeah, let me start share the screen. I hope it goes visible.
Yes.
Great. Fantastic. So I'm Riccardo Fogliera, and I'm in charge for the project and program management inside MDLS team. We are one of the group that in Applied Materials are running the software business, basically. And what we have is a simulation software that is called Ginestra, that is based, that has inside a material library mainly, that we use for the random simulation. So I would like to go through it quite, let me say, it will take not so much so that we can cover basically both parts. So what is Ginestra and why we use a material library inside Ginestra. So starting from Ginestra, Ginestra is a simulation software that takes care of running simulation at device level and mainly simulating what we have as a main relevant electrical parameter for a device like EV curve, CV curve, etc. So Ginestra, the strength of Ginestra is that it is a material-centric simulation software where we rely a lot on the material properties and all the, let me say, parameters that are connected to the electrical transport and that can interact and can impact the electrical transport in order to basically map the reliability of the device, so projecting what will happen after a certain number of cycles, electrical cycles, or anyway, what is the effect of maybe noise, changing the electrical characteristics, etc., in order to make, let's say, a kind of map and simulation of what may happen to the device that is under analysis. With Ginestra, yes, please, some questions? Okay, so with Ginestra, we can cover a certain number of applications, and here I report what we have as a, let me say, main families of the device we can simulate. And you can see basically what we have in terms of logic, but also memories, also emerging technology. So we cover some PCM memory, ferroelectric memory, etc. But also we are exploring also now the ICAPS area where we take into consideration power or LED, etc. So mainly what we do, so with Ginestra, is to run a material to device simulation that help and will help the early projection and understanding of what will happen into the device. The normal usage of Ginestra goes on in two main paths. One, the design, and the other is the learning. So when we talk about design, we start with the device. We create it, so we assemble it. We put the geometry and so the shape, and we put the material with the related properties. And in this way, we make the setup, we prepare the test, we identify what we need to simulate, and we run the simulation. The output are yes, please. Output are distributions, so maybe breakdown and distribution, so Weibull distribution for the breakdown, or maybe EV or CV curve, and anyway, what is helping to the study of the device we design. If we consider the learning path instead, the learning workflow, in this case, what we do is the opposite mainly. So starting from real measurement, so electrical data, like EV, CV curve that are taken from physical measurement, we can put those values inside the Ginestra engine, let it digest, and what we get, for instance, are a kind of distribution map of the defectivity inside the stack of the device, or geometrical characteristics and information, so that can give, that are related, that are connected to the kind of measure we took as input. So that is another strength of the tool, that is able to map what we measure as physical values, physical waveforms, into into device characteristics that could be geometrical or material related.
So this is not limited to electrical, could be stress, thermal, whatever, correct?
Yeah, we are extending now this metrology path from electrical only to also optical measurement, for instance, or as measurement. So this is this is a, let me say, workflow that where we see value, and we are improving that the kind of analysis in order to integrate much more the information we are able to extract.
So Ricardo, you said you're doing simulations initially to come up with the properties. So this is like physics simulation on the actual material. Correct. Chemistry and
correct. Yeah, it is a based engine. Correct. Yeah. So we run simulation that are physical simulations. So the interaction between atoms, so defects inside the material that can facilitate the current flowing and carrier transport.
All right. So this is your own simulation tool that does the simulation, or is it a commercial simulator?
No, this is what we develop and we sell. So this is a tool that it's owned by us, and we sell it.
Okay.
Mm-hmm. So is that a Schrodinger equation, or is it like a more like a classical physics-based solver, Ricardo?
It combines both. It combines both. So can combine Schrodinger plus Poisson. There is diffusion. So.
Okay, and then you sell the simulation tool to customers as well.
Yeah, exactly. So we sell to customer. We use also internally, but it's a matter software. So yeah.
Okay.
Okay, so here I'm just recapping what are the kind of technology we are supporting at the moment. So as you can see, logic, so gate-all-around, memories, DRAM, NAND, and also the emerging technologies. And this is a picture, a cartoon of the functionalities we have connected to Ginestra. So if I recall what we said before, in terms of learning path, learning workflow, this is the defect spectroscopy. So it is able to give maps of defects, for instance, coming from electrical measurement. We go run simulation on reliability. We are compatible with some of the tools that are also used during simulation, that are not only Ginestra. In order to speed up the computing of the certain equation, certain part of the simulation that may take longer, especially for the reliability, we also support cloud computing, so parallel computing in general. And going to the right corner, we see here the material library. So as I was saying before, Ginestra is a material-based simulation, because the material and the properties of the material are playing an important role inside the simulation. And this is why we have a material library that is at the moment embedded inside the simulation, the software.
One more question, Ricardo.
Yes.
Can you go back to the previous slide on the material library, right?
Yeah.
The material properties that you're looking for are all, like in a nano dimension scale, like defect density, maybe the energy gap or whatever, right?
Correct.
So the material properties that usually that we have been dealing with in the MDX has always been on the macroscopic level, like probably Young's modulus, conductivity, electrical conductivity, dielectric permittivity, kind of a thing at a macroscopic level. So, but I also saw you do a optimization between process to material to devices in your first slide. So, do you intend to map any of your material properties to a macroscopic level, or basically, I'm just saying that we are all talking about materials, but at two different scales. Just trying to see where the disconnect or where the connect comes.
Correct. So at the moment we are exploring also the way to connect the process down to the electrical performance. We are not yet there with the managing also the properties at a macro scale. So at the moment we are still on the smaller scale that are related to the electrical simulation.
Okay. Yeah, but nevertheless, you still will benefit from the common data format and everything, right? That should that's a problem that's shared by both of us. So this forum could help in those regards.
Yeah, sure. Okay, so moving on, just now zooming more on the material library. So basically, as I was saying before, Ginestra relies a lot on the material properties. And so if you're supposed to start a simulation picking up a material for the device you want to simulate, and you run the simulation, you generate your distributions. Those distributions are normally giving you information on how it should behave the device, and so you understand how you should maybe adjust the properties in order to change to stay inside the specification for the device. So when we look to the process, we may adjust process according to what we saw as output from the simulation. That is for sure measured at a certain point, and if we recall what we said in terms of learning flow, this measurement can bring to adjustment of some material properties that can also be simulated again in order to see if we go back into the proper specification track of the device. So this is mainly the flow where Ginestra is tuning the properties, the material properties, and using them in order to run optimize the simulation. The material library can be fed in several different ways. So if we start from scratch without any kind of data, we can rely on public databases, literature, so look into articles, values that are properties that are present in articles, and also have initial simulation like DFT, molecular dynamics, etc. So that is one source of data that we have for the material library. Another source of data can come from experimental. So as I was saying, what we do with the effect spectroscopy is to extrapolate the material properties from the electrical curves that we give as input to Ginestra, and that are also used to populate the material library. Once we go to run the simulation, so we pick up the material from the material library, and we can use the property according to the kind of simulation we want to run for the certain device that we select. Because, for instance, if you want to pick one device and maybe you are interested in a kind of simulation, does not mean you use all the properties, but maybe you can use just a subset of properties that are relevant for the that device and that kind of test you want to simulate. We at the moment are structured with XML format for our material. So basically, it's an XML database that has around 70 materials, and each material can count up to around 300 electrically relevant material properties. So those properties, basically, if you want to have a look on them, part of them, it's let's say can be grouped in main types, let's say, and divided in subgroups. And as I was saying before, for all the when we run a simulation, maybe we do not use all the properties we have for a material, but a subset of them that are the relevant one for that kind of simulation. So this is, let me say, to give a picture of the complexity that is behind, anyway, this kind of simulation world, and the importance also of knowing the properties of the materials to be able to do the proper prediction and simulation with Ginestra. So in this case, we consider not only pure electrical properties, we may take into consideration some thermal or mechanical properties according to the simulation we run, because we can maybe also simulate the temperature distribution inside the device, for instance, when there is a current flowing through it. So it is important as well to know also some thermal properties of a certain material to have the proper thermal distribution. So that's basically is the overview of Ginestra, and how the material library that we have, what is the role that the material library we have plays inside our simulation software.
Great. Thank you, Richard.
So the target user of these libraries would be kind of a fab, somebody who's actually building the devices. Is that correct?
Correct. Yeah, the TCAD engineers normally that are designing the device, and they want to see what is the behavior of it. So trying to understand what is the proper thickness of a film that will be deposited, or maybe find the proper material to obtain a certain characteristic, a certain distribution, or identify the proper dielectric to improve the breakdown reliability, for instance.
Right. So as Lal was talking about, we're more interested in kind of the macro material properties, primarily for multi-physics simulation. So it looks like some of these properties can be used for that, but
yeah, maybe there are in between of these 300 properties that there could be something that can be used also at that level. To be honest, I do not know I do not have the full picture here now, and I cannot recall.
Yeah, so I'm wondering, is this a subset, a superset, or is there a Venn diagram?
So the bulk properties that he has mentioned, Tony, we are a subset of that. So for example, he mentions resistivity, right, which is basically conductivity, right? So that's where we belong. But where we do not have is doping ionization, for example. That is something that we don't mention in any of, we don't talk about at that level. We're looking at a more macroscopic.
Yeah,
a subset of that one.
Right, but I'm saying it is do they have all the properties that we can choose the subset that covers our needs, or is there stuff missing in these properties? That's kind of what I'm asking.
Yeah, okay. I don't know the answer to that question, Tony.
Yeah, so we need to define our list and reconcile it, right?
So, yeah, that's correct. We have to do it independently.
Yeah, I missed the last call. Do we have a first cut at a list of the properties that we're interested in, James?
Yeah, we do have, I think, let me share that what we have so far. I think, but definitely that is not inclusive. I think that was like some questions brought up in the last meeting. I think move to, I think, brought that as well. I think how extents that we want to cover. I think we do have that high level. Give me a second, open that documents. I have the spreadsheet that I kind of created based on the last couple meetings that we had.
Yeah.
I think that's.
Hi there,
Go ahead.
Tony. It is Andrew Miller from Answers here. Yeah, so I did a quick review last time, and I think my suggestion was that for the electrical and thermal, I think you'd covered them, but when we get to the mechanical, I think it's important to define the kind of scope, because when you're going to multi-physics simulation and you're thinking about structural simulation, it's what kind of scope. Are you just going for elastic linear, or are you going to try to model non-linear mechanical properties, or are you going to try to capture failure modes, which are can be quite specific to different types of materials. So I think from that point of view, we need to decide what's the kind of scope that we want to deal with, because as soon as you get to these non-linear properties, then you then start to get to solve a specific models, which is quite difficult if you're trying to have a generic.
James, don't make it smaller, James. That's not. Yeah, just zoom. Yeah, just go up to E. We can scroll down. So we have thermal. Well, that's thermal mechanical. So this really is kind of the warpage type, right?
Yeah, I think like the thermomechanical, I think a lot like the rate thermal related, and then some stress. The tensor and things like that, and then we do have that the glass temperature, transition temperature, and they're all mechanical related. And then we have the electrical, mainly. I think these two are the main major area. We did talk about packaging substrate components. Like each of them, I think like PCB, silicon, and substrate interposer. I think there are different material requirements there. We never really go deep in discuss the two of these things. They may think kind of overlapping, but there's some of these things when I go and research on it, they're kind of each of these components definitely they have a kind of specific kind of like material properties, right, like hardness and things like that, right? So and then we have like all other things that we haven't kind of like it's generalized right now, so not go into those. I think we talk about the reform profile, the more materials, right? The bondings, like the via materials or TSV materials, like conductivity rules and all other things here. So I think that's what we have.
So those are the different elements or components that we want that we need the material properties for, right?
Yes.
And it's probably you probably don't need everything for all of those, right? So we probably need to create a matrix. Have we kind of looked at what's in the JEP 30 standard, because they do have material properties, so that's probably a good starting point. And most likely we're probably going to end up doing a JEDEC standard on this, and for consistency reasons, we want to make sure we're not conflicting in terms of structure or terminology with anything that's in the JEP 30.
That makes sense. I think that when I went into that materials, I think I especially in the part model, so I probably need to look into that. Anyone here has looked into the JEP 30 like material properties or JEDEC material properties?
So I think I'll take that as a no. So I think we should take an action to have Michael Durkin maybe provide a summary, and we should look at what's in there, because that's probably a good starting point, and then decide what's missing.
Sure, sounds good. Yeah, I will also look into that as well and see what they have there. And I think like that JDEC probably a good starting point. And
Does anyone, you know, on the call here have any objections in working with JEDEC on this?
Oh, that's
not from my end.
Well, I mean, anybody on the call. So unless anyone objects, I think that's probably the direction we're going to head.
yeah. I would no objections, Tony. I would add on the general list, right, all the heat materials, right, like that tin 1, tin 2, those things I will add as well to the list, just so that those have to be captured somehow. I think there were 28 captures it, I think, but we'll make it more explicit.
Yeah, I mean, you have cold plates and, you know, heat sinks, so metal. Yeah, we should be a little bit more clear on the terminology.
Yeah, with the thermal interface materials, that's the pretty. That is something that will be needed there to conduct the heat.
Okay.
And
So Ricardo, you mentioned you have these material properties in an XML format.
Sorry, can you say it again, please?
Yeah, you said you have these material properties, you know, in an XML format.
Yeah, at the moment we use that as a format to manage that property. So inside our simulator, yeah.
Okay, and you I suppose I'm not sure if you know whether or not that's compatible with JEDEC or is it a proprietary format?
Oh, well, that is more technical information I can retrieve from my colleagues, so that are in charge of the development. So
Okay, so yeah, so the goal here really is to what we're trying to establish here is to define a list of material properties and create a format to describe those material properties. The actual values is, you know, these are kind of the containers where the specific material properties go. So we're just trying to provide the general mechanism to be able to capture the relevant material properties. So we're trying to come up with a list of the relevant properties, and that list, you know, is going to be the work in progress as the technology changes. You know, we'll be adding to that, but we're trying to come up with focusing at least initially on some of the important properties that are necessary for some of the programs, these 3D HI programs that we're working on with DARPA. Is probably a good starting point, and it does include some optical and RF type of analysis.
Yeah, I mean, but then for the scope of this, I mean, what is the scope? Because, you know, there are a large number of properties which, you know, some will be relevant, some won't be relevant. It really kind of depends on what the use cases you want to use these for.
Yeah, I think we probably need another sheet here. And maybe the way we should structure this, James, is have them a sheet for the components, right? Have a list of all the different, you know, things that we want material properties for. I would put that maybe in a separate sheet. And then I think we probably also need maybe a summary of the analysis that we want to do.
Another sheet for the summaries analysis.
Yeah. So we want to do thermal analysis, you know, stress of the optics. So you use the industry standard nomenclature for what we call these. You know, there's the general category is multi-physics simulation, but let's create an explicit list of the different analysis that we want to perform, and just and then the properties, there's I'm sure there's some overlap in the properties, but we can even have a lookup table that shows, for this type of analysis, you need reference the list from the actual properties.
Makes sense. So including all the predictive everything, like SIPI, whatever, right?
Yeah, so we've got the ANSYS guys in here, and Lal representing Siemens and Cadence. So if we could collectively decide on that master list of the analysis.
Yeah.
So I think it's from an EDA perspective, that's what we're looking at. So I think we should look at each of us and decide what analysis we're trying to define the scope of the materials that we want. So we need to bound this. So there's optical.
Yeah, makes sense. Let me share the link with everyone. I think and maybe you guys can feel free to add on it. I just
please share. So Andrew, I just want to address your question, right? I think what Tony is saying, I don't know if he got the answer. We really do not know what is the exact scope, but I agree with you. Like you said, mechanical is the one that goes from a linear all the way to anywhere, and non-linear, it can stretch you there, right?
Yeah.
And there are applications, if you go for reliability applications that you mentioned, right? Like we see that wire bond coming out, especially in power electronics, and I see this all the time. Most of the customers want a very nonlinear simulation there for mechanical stress analysis. So that's the space, because we see those things needed, but how much is needed at the early stage in this kind of application is something that is not very clear to me. I don't know if it is clear to anybody else as well. So part of this exercise is to come up with those materials, come up with those analysis, and kind of have experts like Li Hong who practices these things to kind of tell what kind of a nonlinear mechanical analysis they will need, and based off of that, what kind of material properties that would entail. So I think this is still work in progress.
Yeah.
We should at least keep the door open.
Yeah, I think I see Zane is on the call representing Intel. Zane, I know you're not a multi-physics simulation expert, but certainly Intel has a lot of those folks, and you work with them. Would they be willing to help kind of define the list of types of analysis they do, say, in the mechanical and thermal? Can we kind of get a list of
I can check on that, but
just a generic list? We don't want anything proprietary, but kind of
yeah, I can check on that. I'm not sure,
because I know you guys you with the high volume stuff that you do, you probably do a lot more analysis than most companies. So I think if you put that list together, it's probably going to cover pretty good cross section of the industry. And then there's probably different. I'm sure you guys are doing optics, but I'm sure there's other inputs that we're going to want to complete the list.
I can check. I'll let you know.
Okay.
Yeah. And then the kind of third axis here is, what for those properties for those particular use cases,
right?
What do they vary with? And so you can have everything varies with temperature. The electrical properties will also vary with frequency. Some of these properties will be some of the materials we're talking about will be orthotropic, so they'll have different properties in different directions, and so so if we try and capture that as well.
I think
space or radiation, I don't know if that needs to be factored in, whether that affects some of these properties, and you know, there's some cryogenic type things where, you know, that there may be a whole different set of properties, right?
Yeah.
and-
So we have another sheet for that. For that dimension.
Dimension.
Well,
Well,
I think it's kind of, I think it's an extra piece of information on those properties. Once we get a property list, we can then go through that list and say, well, these are the kind of things that you have to also capture for these properties. So it could be temperature dependency, radiation dependency, whatever other factors we need to put into there. So
Yeah, you know, the way I would, so Tony, our final product here is going to be the formatting, the template, right? Like a CDXML, what is that, the format for specifying material properties, correct?
well, I think yes, but it's really the templates that we're building, right? That's really what we need to define. Yeah, right.
So I
And
would,
then,
you know, the way I will approach this problem is, you know, we cannot list out all the properties, all the things that we need, but we can build a basic building block that will pretty much cover everything. You know, what Andrew mentioned, like X, Y, comma data, like this could be your dielectric constant versus frequency. That is something that's a 2D table that we got to have. That is something we got to have. He mentioned anisotropic property, XYZ direction. I will say for this basic building blocks, if a property varies as a function of space, we got to have a format for that. If a function varies as a function of frequency, there should be a format for that. If these things are not like innumerable, these are all finite number of things. If we define these things,
right.
Any other property that we bring in will fall into one of these categories.
yes, that's right. Yeah, I think you're right. We need a generic way of describing these properties, which can vary by one or more parameters. And once you have that, you can then reuse that for any property which you need, but you've always got a generic way to store it, which can deal with the very simple ones, you know, like a single number, all the way through to a kind of a set of properties which, you know, change with, you know, 2 or 3 different parameters. And as long as you make it generic enough to cope with the very simple all the way to the most complex, then that's the way to go.
Yeah, and except of course when you talk about non-linear, then that depends on excitation and all those. That makes it a little bit harder, but at least insofar as linear is concerned, this list will pretty much cover most of it. That's the building block that we should focus, and then that should, like you said, that should cover pretty much. We'll keep adding those to the basic building blocks.
yeah. But again, I think we do want to let's start. I think we should start and look to see what's in JEP 30, and I can ask maybe Michael Durkin to provide a summary of that for the next meeting. And I think it's going to be a good starting point, but I'm pretty certain that we're going to have to expand that. So that'll at least kind of give us a good flavor of the structure of how we want to capture this stuff. And ultimately, if we're going to go JEP 30, it's going to have to follow that structure. So we don't want to, you know, kind of build this thing to be incompatible out of the chute. Does that make sense?
Yep.
Okay. All right. I'll reach out to Michael James if you could add him to the. Are you or David maintaining the invite list?
I think David is now, but I check with him, see we can also.
Okay. Okay. And Zane, is that something maybe we could try to do in 2 weeks, or I know once Michael gets going, he's probably gonna take the whole hour. So maybe next 4 weeks from now, that'll give you a little more
4
time.
weeks. Yeah, because I'm already committed for next week for the other stuff. So
that's true. Yeah. Okay. So why don't we just kind of, yeah, good. You're a step ahead of me, James. Thanks.
Yeah.
So
Well, we have lots of Michaels, so
Oh.
Michael Durkin.
I think if I spell correctly.
And then Mike Lafferty will have the action to write all this up, right, Mike?
Yeah, perfect. Thanks, Tony.
Okay.
Shall I add that?
No.
I wish you said yes. So okay, that's good. And I said, do you have anyone take action item on the components, or everyone just going to add on these components then?
Well, this is a Google Doc, right? So I would encourage, you know, some of this subject matter experts on the call here to feel free to, you know, add
Add it.
stuff and you know, you could add comments if there's stuff that, you know, and so I think we should try to start building on this.
yeah, it'll be good to share that thing can populate it. And what parallelly also, Tony, for things that we know for sure, right? Like frequency dependence, we should look at the format CDXML and see if it supports it. If not, we have to extend it.
Yeah.
So I think that effort can start parallelly. So we don't need to wait for you know, some of the other standards. These things we know we need it. We should parallelly look into those things as well.
Okay.
Yep.
So okay. So everyone has a list, right? So I put in here as well. I share on the chat. So I think I please feel free to add. So that's good.
Also in this document, right? The last time Micron, Western Digital, I think Muthu was from Western Digital. He had a question regarding as to what is the objective of this working group, right? Is it for standardization or is it for defining a template for exchanging materials? I think it will be good to, as we write these documents, right, like a kind of tell a bullet point, this is what we're trying to write, like a summary kind of a executive summary kind of a thing, so people can read it.
Yeah, that's a good idea. Just put it right in a mini mission statement, if you will.
Yeah, at the top level before even anything begins.
Okay. Anyone want to take action item to write that, or maybe I should write something?
I can take that one.
Okay.
Yeah, I think Tony should.
I'm going to start at this boondoggle. Yeah. So again, just kind of you know, informally, what we're trying to do here is capture or define a format for describing relevant material properties to support the analysis necessary for 3D HI systems. You know, that's the high level, you know, 1,000-foot view of what we're trying to accomplish here. So you know, we want it to be machine readable. So I think you know, XML is important. We want it to be open source. So these whatever we publish here is open source, but it's read only. So you know, anybody can view this from the outside world, but you know, we want to limit who has access to change these formats. And the goal is, you know, that it's usable. You know, once we have a kind of a first cut, people can start using it. But the goal is to get formal sponsorship from a standards body. Most likely JEDEC is the direction we're leading. And that takes, much longer time frame. So we don't, we want to make sure people can use this before it becomes a standard. It may be a year or more before this will become an official JEDEC standard. But we need something working right now, and we are collaborating multi EDA vendors specifically in some of these projects to have a common set of design kits, and one of those kits is this material design kit properties.
Okay, thank you, Tony. I think last weeks the only difference was the discussion was around standardization or coming up with any format. I think you're touching upon that topic. I think there are many formats available. That's what the Western Digital gentleman told. They're all mission readable today, but they're all, from what he described, they're all multiple different formats there. Proprietary. Right. We have to standardize.
We want a single format. We don't want to take a proprietary format from any vendor. We want to have a single unified format, and then I think it should be relatively straightforward for each of the tool vendors to be able to map into their specific formats. And the other thing from the material guys who develop the materials, characterize the material properties, again, this would give them a mechanism to put their relevant material properties into the format, right? So that's it's so they don't have to support multiple tools. They just put it in this format, so it can come from multiple sources to create the rules, and then multiple analysis tools can consume it. And I think that's going to make life much easier for all concerned parties, throughout the supply chain. And that's what we're trying to do, is promote a chiplet ecosystem. So I think that's kind of the spirit behind what's driving all this.
That's good. Thank you, Tony.
Okay. So these are active hyperlinks. So they're typically distributed in the meeting invites.
Yes.
James. Yeah.
Yes, that's right. Yeah, all documents here are invited here. I think there's a document, and then there's they kind of overlapping each other.
And I know I have had problems with our email tool. It doesn't like Google Docs, or it actually not email, just my web browser. It doesn't allow us to. I can get access to the folder, but if it's just a hyperlink to a Google Doc, I've had issues where it gets spammed and I can't access that. So so I think if we have kind of a folder directory structure to organize this, and then we send the links, that I don't know if anybody else has had problems, but I've had problems.
There's this folder here. I think you want to go directly to this folder. That's all the.
Yeah. So why don't you pop that, and let's just see what that looks like.
Yeah, all should be in here. Documents, but maybe a bit, or including like the presentation that we have in the past. Let me share the link here in the chat.
Yeah, maybe we could add another level hierarchy just to kind of organize this a little better. Otherwise, this might get unwieldy.
Yeah. Even now, I make out.
Like status, or meeting notes. So you can have that in one section, and then
just put documents there, I think, so that we're focusing on the one that we're editing.
All right, we don't have to do this now, but
yeah. All right.
And so these, so the minutes, I guess we're just appending, right? So it's one document and you just, so all the minutes just get updated.
Yes.
So it's just a single doc and you just keep appending to that. And I guess the latest updates are at the top of the document.
Right.
Yeah. I think if you go to the meeting minutes, I think that should have everything linked from there on top. But if you go to this folder, I can share this folder. Is that okay to you, right? This way?
Yeah, that's fine.
Okay. Let me share this folder. Let me put into the chat room here. Let's see.
No, when we actually start creating the XML files, we'll probably have a GitHub or something to put this in.
Sorry, what
do we for the CDMXL stuff that
Yes.
we use?
We do have a GitHub, yes, for that.
Yeah, so we're going to set up a separate one for MDK.
Yeah, I think that makes sense.
Okay.
It's a CDX version. I think we can set another one, yeah, for the.
Yeah.
We'll put that in the notes and get them set up.
Yeah. Yeah, we're not quite ready, but you know, eventually that's where it'll go.
Yes.
Right. Anybody else? So I did meet with a gentleman from a company called Z0, Bill Hargan. He's interested in joining the group. He's got a small company that has a database of material properties, and you know, he's willing to work with us. And
What's the name of the company of the person?
Bill Hargan.
Hargan.
I'll send you his contact information. I forwarded the previous invite, but he wasn't available, I guess. I asked him if he was going to attend today, but I can ask him to present. But I guess the next couple of meetings we have an agenda item, so we'll see. We'll try to get him on the agenda at some point.
Okay. Sounds good.
Great.
Yeah, and in encryption. So once we have, you know, the formats and the templates obviously be open, but when you put the data, I think it is important that we have the ability to encrypt the models. So, James, is that something that we did for CDMXML, or is that something we need to look into?
We have to go into it there.
Yeah.
Okay.
The public encryption and decryption that can also be proprietary at the end. So we just want to.
Yeah, because this stuff, I think material vendors in general would probably consider some of this information, more so probably on design rule kind of stuff. But I would suspect material properties. I don't know, KK and Ricardo. I mean, what's your take on that?
I'm a sponsor of encryption in this case, so yeah.
I'm sorry?
I'm a sponsor of encryption, so
Yeah,
for the
yeah. Because,
absolutely.
you know, you probably don't want to share your material properties with your competitors and vice versa.
And normally they are felt as sensible IP data. So yeah, definitely encryption there makes sense to be at least considered. So
Yeah. Does your tool support that?
partly yes. So there is part of the code that supports encryption. So for the most relevant data, yes.
Okay.
There's something called XML encryption. I probably need to look into it and see like what does that actually mean and cover.
Yeah. Yeah, I know the Z0 said they do support encrypted XML models. So but probably the standard templates will just have some, or arbitrary generic values for some of these material properties. And
Yeah, you're talking about the entire document encrypted, right? Not part of
no, well, I'm talking about the specific material properties. So when this the material vendors are going to provide the properties to their end customers, which could be, it's going to be a designer, right? And we just need the ability to encrypt that. So there may be proprietary equations and models that they don't want to share, and yeah, I think that is going to be a requirement.
Yeah, it can be part of the document or the entire document. James, we have seen that in the circuit simulation world, so we should be ready for that. And I think the key will be like when they encrypt it, what software they use, how do they decrypt it, and if there is IEEE way of doing this, then it becomes easier. But we have to figure out the details. But I think that is needed, and it could be part of the entire document.
Makes sense.
Okay, well, very good. Thank you, everyone. We'll see you in 2 weeks.
Yeah. Thanks, everyone.
Thank you, guys. Bye-bye.
Thank you. Bye bye.